Okay, welcome back, and in today's session we are going to look at practical cryptography. When we went through the slides, there were certain concepts which are hard to visualize. How come symmetric encryption requires only one key, asymmetric requires two keys, and how come hashing is only one way, and in what circumstances we would actually use encoding. So in today's session, we are going to look at the Linux command line. We are going to step through some Linux commands that actually perform these functions, and hopefully it will give you a better idea to visualize what are all these functions actually doing. Okay, so let's get started. So the first thing we are going to do is we are going to echo something secret into our message or text, and this is what we will actually use to encrypt and perform all the functions later on. Okay, and this is what we are doing. Actually, we are echoing everything and we are saving it in this file called message or text. And we can actually use this command cat message or text to actually view what's inside it, and it's exactly what we saved in the previous command here. Okay, so we're going to take a look at the first function, which is to use symmetric encryption, AES, to actually encrypt this message. And the first thing we need to do is actually to generate the key. So what we're going to do is to use the OpenSSL command, and we are going to save it out to save it as output into this file called AES.key. And what we are going to do is save a 32-byte key, which is 256 bits. Okay, and after we have done that, we can actually view the contents of AES.key. So we are going to use XXD here instead of cat because AES.key is a binary file, and this is the contents actually, or the key that we are going to use to actually encrypt in future commands. Okay, so let's start the encryption now. So we are going to use OpenSSL again, and let me run through the command. It looks a bit daunting at first, but what we are going to do is OpenSSL, we are going to encrypt, and then we are going to use this cipher, AES 256-bit and the CTR mode, counter mode. So there are a lot of different kinds of modes, and I won't go into detail now because this is really a more basic kind of a level. And then what we're going to do is we are going to put in an input message or text, which is this message earlier that we have saved, and then the output itself we are going to output the message into this file called message.enc. Okay, we are going to use a key file, and then it is this AES.key file. Okay, we are not going to use a salt for this encryption, just to make it simple. And the initialization vector is something that we need to specify, and it's something that is sent along together with the encrypted message, and to decrypt it we need this initialization vector again. So this is just a randomly generated initialization vector. Okay, so once we do it, there's a short warning here that other functions may be more appropriate, but for today's context, we are just going to use AES 256, because this is something that's covered in the certification exams, and we just keep it simple at this moment. Okay, so after we have done this, we can actually take a look at what is inside message.enc. Okay, so what we can do is again run XXD and then message.enc, and we can see that now our message, which was plain text, was something like this. It can be easily readable, and it has become encrypted. And someone who intercepted this will not be able to actually read what the message is. Okay, so now we'll demonstrate symmetric encryption, which is how we can actually decrypt using the exact same key. And so I'm going to paste in this command over here. Okay, so it's almost the exact same thing, except now we have a -d here. We are telling OpenSSL that we wish to decrypt this time. Okay, and we are passing in the encrypted message as the input now. Same key file, same no salt, and same IV. Okay, and let's see what we get. Okay, same warning, but now we get back the same plain text that we were trying to encrypt earlier. So this shows that after you have sent this particular encrypted message to someone else, they can actually decrypt using the exact same key, AES.key. Okay, so let's do a little bit of theory crafting here. What if we try to decrypt this with a different key? Okay, so now I'm going to use OpenSSL again to randomly generate a second key, same length. And then if you take a look at the second key, okay, it's totally different from what we have for the first key over here. Okay, totally different. And then now if we try to decrypt, using the second key, but with the same IV again, let's see what we will get. Okay, we seem to get gibberish over here, and that's because you use the wrong key to actually decrypt. So sometimes an error may appear. Sometimes you get gibberish depending on the cipher mode that you have chosen. But this shows that only when you use the same correct key to decrypt will you get back the correct plain text message. Okay, let's take a look at the key here. So when we take a look at the key, let's see, where's the key? The key is over here. Okay, So this is binary key, and it's not really something that is easy to actually transport. Over some protocols like HTTP and all that, it only supports plain text. So how do we transfer binary? Things like images are also binary. So this is where encoding comes into play. And okay, let's quickly take a look at what happens if we use cat to take a look at what's in AES.key. Okay, we get a whole bunch of gibberish here, and we cannot actually send this gibberish, because if we send this and we copy over this gibberish, it will not be the same, because the binary bytes are not actually accounted for properly. So what we need to do is encoding. So one of the forms of encoding, the most popular one, is base64. So what we do is we cat AES.key, and then we pipe it to this base64 function over here, and it immediately gives us this really beautiful plain text thing that can be easily transmitted over here. So I can actually copy this, and I can send this to someone else over a secure channel, because we are sending the key, remember, and then someone else can actually have access to this key, and then they can paste it back into base64 and pass in the decode function over here. And when you do that, you actually get back the same gibberish here. And this is a secure way, this is a safe way to actually transfer a binary object without there being any corruption taking place. And so we have demonstrated that this is the purpose of base64, is to change the format of a certain file from binary to text, so that it can be more easily transported. And take note that we didn't pass in any key here, we didn't generate any key here. Anybody with this base64 function, this command line, can actually perform that decryption, can perform that decoding. Okay, so we've taken a look at symmetric encryption, we've taken a look at encoding and decoding. So let's quickly take a look at asymmetric encryption, which requires two keys again, the private and the public key, as we explored earlier. Okay, so we are going back to our old friend OpenSSL, and what we are doing here is we are generating a private key. It's an RSA key over here. This is the algorithm we specify, and we actually save the key into private.pem. Okay, and then what we are generating is a 2048-bit RSA key. Okay, there will be some randomization going on before it generates it, and then we can take a look at what's inside the private.pem. Okay, so interestingly enough, if we take a look at what's inside private.pem, we notice that it's all in text. So they would really want you to be able to transfer it easily. So actually what they have done is base64 encoded. So if you see equals at the end of it, just as we saw here, we saw equals here, it's very likely going to be base64 encoding. So this is what they've done. They've saved the private key and encoded it in base64. Okay, so what we need to do is to use RSA to actually pull out the public key from the private key over here. So we want to pull out the public key, and we'll pass in this private key that we just generated, and we'll save the public key in a separate file. Okay, so this is done now, and then we can take a look again at the public key, and we realize that the public key is a lot shorter now, because it's a segment, it's part of the private key. Okay, so this is what we can actually put this on our website, or we can publish this on anywhere, and then anyone with the public key can actually encrypt a message and send it to us, and we are the only ones who can decrypt it, because only we have the private key. Okay, so now let's assume that we are trying to use this public key to encrypt a message to be sent to us. So this is someone else that's encrypting the message. Okay, again we are going to use OpenSSL. What we are going to do is encrypt public key utility, and then we are going to put in this public key here, in key public.pem. So we are going to use this public key. We are going to encrypt the same message or text, and the output we are going to save it in secret.enc. Okay, let's run this, and immediately we can see what's in secret.enc. So if we look at secret.enc, okay, it's a whole bunch of gibberish here. Again, nobody without the private key, you won't be able to decrypt this. So you can send this over to whoever who has a private key to actually decrypt this. Okay, and now we are going to actually decrypt this for real with the private key. Same command, key utilities, and then we send in the decrypt function now, because now we have this encrypted blob here, and then we are going to give in the private key, and then we are going to pass this in, and we should get back our plain text message. And indeed, this is what we are getting over here. This is what we actually encrypted. Okay, just for sake of playing devil's advocate, if we were to try to use OpenSSL and we pass in the public key instead of the private key, can it be decrypted? So the answer is no. So there's an error over here because we cannot actually read the private key over here. OpenSSL, has recognized that in order to decrypt, you actually need the private key, and this shows that how asymmetric cryptography actually works. You use the public key to encrypt, and you use the private key to decrypt. Okay. And finally, once we have done with all of this, we take a look at the topic of hashing. So hashing, as we recall from the session earlier, it guarantees integrity, not confidentiality. Everything we looked at so far is about confidentiality, because someone who receives this bunch of gibberish here will not be able to read whatever is actually the plain text of it. So when we look at hashing, we are not doing any functions on that will affect the plain text itself. Okay, so we are going to take a look at MD5 sum. So MD5 is one of the hashing algorithm, and we are trying to hash a message or text, and this is the hash that comes out. Okay, so this is a 32 character hash, which is 128 bit. Okay, let's see what happens if we try to hash a different message. So now we have almost the exact same message, but it's just missing this last star at the end over here. Okay, we save it into this file message2.txt. Okay, and if you try to calculate the MD5 sum of message2.txt, we get a totally different value over here. So this shows that once you have tampered with it, you've changed even one single character in the contents itself. The whole hash would actually change. One thing to take note: if you change the file name, the hash does not change. Okay, only if the contents of the file itself is changed. Okay. Apart from MD5, there are also other hashing algorithms. So one of it is SHA-1. So SHA-1, if we calculate it, it gives us a 40 character hash. And 40 characters would actually correspond to 160 bit hash over here. Okay, exactly same thing. One thing to take note is also that the hash function will always give you the same constant character length. That's why we can always say that MD5 sum will always give us 32 character, regardless of how long or how short the message that we are trying to hash is. You can see here, the hash function is, the message length is different, but actually we get the same output out. So this shows that hashing is actually one way, because you cannot possibly hash a super long file into something like this and then expect to actually get back the long file. Otherwise, you can actually compress infinitely long files into a 32 character hash, which is not possible. So this shows that it is actually a one-way function. Okay, so now we are going to take a look at our very last hashing function, SHA-256. Okay, so SHA-256 is actually something that is much more secure, or something that's more contemporary in contemporary usage. So you can see it's super long now. It's 64 characters or 256 bits. So what we've done earlier is to actually save this into this file checksum.txt. So if you can take a look at checksum.txt, it actually contains the hash of the file as well as the file name itself. And so let's do a bit of a let's do a quick checksum. Okay, so when we run SHA-256 sum and then we check this file itself, what's happening is they'll actually try to hash this file again, and you'll try to match to this pre-computed hash. And if you try to run this, it tells you that it's correct. Okay, so what happens if you modify the text over here? Okay, so now I'm going to modify the text, and it's going to look like this. So I've removed all the stars, and I'm going to save it into message.txt. So now when I run this, it will actually try to hash this, and it should not match anymore because it's going to be different. Because the plain text is different. It is already different. So this shows that the integrity has been compromised. So let's see what happens when we run this. Okay, immediately it tells you failed. There's a warning that one of the checksum did not match, because we've modified message.txt already, so it will not match anymore. Okay. So what we've covered today is we've taken a look at very quickly at some of the Linux command lines. We've taken a look at symmetric encryption. We've taken a look at encoding, asymmetric encryption, and then hashing. And so that's it for today. And I hope that you've learned something from this session. And thank you.